Okay, I'm going to go over the paper. Attention is all you need. It's a very fundamental paper, so probably be a long video. So let's just start with the basic old multi-layer perceptron. So what you have is multi-layer perceptron is the most fundamental neural network. So you have a vector which has some amount of parts, so represent those as nodes. And then you have another set of nodes, which, and each of these nodes is going to be represented as a weighted sum of all features in the vector. So I guess in a way, like a usual example is like housing prices. So you can think of this as, I don't know, number of doors. So it's just a vector. So like so say we have number of doors because, a good house has more than one door. So first part of the vector, and then, I don't know, number of like bedrooms, say it'll have like 3, and so on. So you represent that in here. So then you compute a weighted sum of all of these values. So that would be 2 times W1 plus 3 times W2, and so on. And then that gives you that gives you a single value. And I'll call that Y1. This will be Y2, this will be Y3, and so on. You can have as many nodes as you want. So you'll have it'll be a 5-dimensional vector to a 3-dimensional, and this is arbitrary. The number of Y's and the number of inputs and outputs is arbitrary. But I'm gonna assume you have a general idea of how how a feed forward layer like this works, or I'm not going to go into too much detail about it here, but you can see that this is a vector to vector representation. So and one of the problems with that is so say we have multiple vectors, you can't find relationships between those unless you transpose the matrix. So if I were to try to represent text, which is what this paper wants to do, then I have a sequence, and I'm going to use this sequence all throughout the video. So I like cats. And you can't just throw this through a network. You can't just throw this through a neural network if you want to do something on it and get some output. And in the case of attention is all you need this paper, it'll actually output the goal is to translate this to I'm going to say Spanish. So me gusta Carlos. But you can't just throw text in there. Like, how do you represent text in a vector form? And what you can do is you can create a vocabulary. So I'm gonna create a vocabulary list. So this will be my vocab, and it'll have the word I, it'll have the word hate, it'll have the word like, it'll have the word cats, and it'll have the word dogs. So my vocabulary is just 5 words. So this is the vocabulary of the entire model. This is everything it knows about. And what you can do is you can represent this by the indices in the vocabulary. So I can represent the word I as the number 0, the word like as the number, that would be 2, and the word cat as the number 4. And now we're getting somewhere. Now we can actually feed that through a neural network and get an output. This is just, it's just hard to encode a lot of information into a single number. So you can actually encode this as a one-hot vector. So this will be a vector of the same size as the vocabulary, and it has zeros everywhere except for the index where it is in the vocabulary. So in this case, the word I would be represented as 1 0 0 0 0. The word like would be represented as 0 0 0 1 0, 1, 0. And the word cats, cats is 3. That would be 0, 0, 0, 1, 0. And then the word dogs would have a 1 at the end, and so on. So you can represent it as this one hot vector. And then you have a vector representation of the sentence. So the word I like cats will become 3 vectors. And each vector is v long. So I will represent this as a matrix, which is of shape S by V, where S is, in this case, S is equal to 3, and in the case above, where V is equal to 5. So this will be a 3 by 5 matrix. So it'll look like that, in a way. So it's just a more compact form. But one of the problems with this is if I were to use the feed-forward layer on this, it would, so we have the 3 vectors, so this would be I, this would be like, this would be cats, feed-forward layer, and if I throw the values through here, they're going to be independent of each other. So the word I will have a new representation, the word I like will have a new representation, and the word cats will have a new representation. But there is no cross representation. The word cats has no idea. It doesn't know anything about the word I. The word like doesn't know anything about I. So you can actually, so what we use is recurrent neural networks to solve this issue. So what a recurrent neural network does is you have this shared weight matrix, which I'm going to call M, or you have this shared module, which I'm going to call M, and you put a vector through it one at a time in time. So you will put this vector through, and what it'll output is it'll output this hidden representation. And you can think of this hidden representation, so this hidden representation I'll represent as a vector. In this hidden representation, it's just an encoded form of the memory. So we take this vector I, we throw it through this RNN module, and then it updates H. And then we feed the next vector in. So like, we feed that through, and then it'll give us, I'm going to denote that as H1, and then this will be H2. And then this will be a new vector, which is slightly different, but now it has information of I and like. And then you have, and then you will encode the word gatos, or cats, in the same module, and then that'll output H3, which is again another vector. And from here, we want to decode it. So now you use the same exact module, or you can use a different module. I'll call this M2. This will be M1. And then it'll output a word. So that'll be me. And then it'll keep changing the hidden representation. So H4. Because the hidden representation is just a representation of what occurred in the past. So it now knows that. So it may have information of the input sentence along with the word me. And then you actually feed the word me, or you can feed the word me back in, so that it has information of that. And then it gusta, so then I'll put gusta, then H5, and then gatos. So you have this encoder-decoder style architecture. You have an encoder on the left and a decoder on the right. The encoder encodes the input sentence, I like cats, and the decoder decodes a sentence from I like cats to me gusta gatos. One of the there's two big problems with this. The first is if I have a sentence that is really long, so I like cats is really short, but say I have a sentence that has 500 words in it, it has to compact all 500 words into this H3 vector, or in this case it would be H50 or H500. So it has to code all 500 words into one tiny vector. And remember, each of the words is a vector itself. So it has to encode 500 vectors into one vector, which there's not enough space to do that. So that's one of the problems. The amount of information you have to encode into one single vector. And another problem is if you know how backpropagation works, you will have to have the loss for me, gusta, and gatos. And for each one, the gradient will have to flow through this module. And the way it flows through the module, the gradients will be updated several times, or will be changed. Like it'll be, they will continuously be it'll be multiplying each other. And you run into vanishing gradients since they keep, where the gradient gets really small, or exploding gradients so the gradient gets really large. And at that point, you'll get NaN values or infinity values, and it becomes very, very annoying to optimize and very difficult. LSTM's tried to fix that, but you still may run into this issue, and you'll definitely run into the issue where H can't encode the information. So the authors here, so that's what we did. That's what happened before. But now the authors propose a new method, which they call attention. Attention is an encoder-decoder. So they propose a simple network architecture, the transformer based on attention mechanisms, which doesn't require recurrence or convolutions. And that is what this paper is about. So let's look at the attention mechanism, or let's look at the transformer. So as you can see, it has multiple attention parts, and each attention part, and attention is like is very important, and that's what this thing's based off of. The feed forward, the add-in norms, those are kind of a general. So let's get into how the attention part works. So attention is given a sequence, just like above here, the I like cats. Just disperse that a little bit. I like cats. And what it actually, let me draw it over here. So I like cats is a matrix of shape S by V, and I'm going to represent it as E now. So V is the vocab size, but usually since this is really big, you can linearly project it by using a feed forward matrix. So if we have this is S by V, you can throw it through a feed forward layer, and then you get out an S by E matrix just to encode it into, or condense it into a smaller vector representation. And E will be it'll be the encoding dimension, or hidden size, or whatever you want to call it. I'm going to call it E. So it'll be S by E. And in this case, S is equal to 3 for I like cats, and E is some arbitrary number. Whatever size you want to represent each of these words, that'll be E. It'll be a vector of shape E. So this will be our input. And the attention mechanism produces three things. It produces the queries. So it has 3 feed-forward matrices, or three forward layers, and let me draw those out like so. And each of these produces a sequence, or it transforms the input sequence along the E dimension. So it doesn't care about relationships among the tokens, it just transforms each token individually. So this will be S, and I'm gonna call it E, just so that the dimension doesn't change. You can change the dimension, but in this case, I'm not going to. So now you have 3 of these matrices, and what these are called are queries, keys, and values. So the queries and keys matrices, they are multiplied together along the E dimension. So you're taking the inner product between the queries and the keys, and you multiply these together to get a matrix of shape S by S. Let me move this down. So now you have this matrix of shape S by S, which I'm going to call QK. And then what you do is you throw this through a softmax layer, and that's just a normalization pretty much, queries by keys. Then you multiply this by the values along the S dimension. And then, so this will be more. And give me 1 second. I'm going to explain what this represents. And then you output a sequence of shape S by E again. So you actually multiply along the S dimension of the values, which is where you get your kind of cross, or where you get your cross information from, where information between tokens is being computed. And then this is your output. So the output's the same shape as the input, which is very nice, and it's a new representation of the input. So why are these called queries and keys and values? So our queries and keys represent as 3 points. So this will be I, like cats, and each of these is just, a vector of shape E. So 3 by E, just like we have here. So this will be our queries, or this will be our keys, and then we have our queries up here. And in the queries matrix and the keys matrix, each of these words, or encoder representation of the words, outputs a vector. So each of these will be a vector, and so are the queries. So in a way, you can think about this inner product as the keys kind of showing off the information of each word. This is what information I have, and the queries being like, what information am I looking for? And you compute the inner product between the queries and every key. So for this node right here, you take the inner product between that node and I, or this blue vector and I, this red vector, this blue vector and like, this blue vector and cats. And then you get a new vector, which in this case it'll be of shape 3. And it'll be the new representation of I. And it'll have the similarity between the vectors. So in this case, the similarity is completely opposite. So the inner product is completely opposite. So it'll be really low. I think in this case it'll be -1. I think the perpendicular is 0, and that is -1. So, in this case, it'll be, I don't know, some value that is some value near 0, so I don't know, negative 0.1. And then in this case, it'll be, that's pretty perpendicular, so it'll be 0. So the values aren't really related. But I just drew these vectors arbitrarily, so it doesn't really represent much. I just wanted to kind of show you how the queries and keys would be multiplied by each other. So you have this representation for each, or you have this similarity matrix that you form between the queries and keys. So let me draw that out. And remember, the matrix is an S by S matrix, so in this case it'll be a 3 by 3 matrix. And I like cats. So this was the vector I was drawing above, right here, the one right over here. And you can kind of, so this will be the keys dimension, this will be the queries, and you can kind of visualize this as like a heat map. So say the word, so let's say that you want to kind of find information. So the word I wants to kind of find information. I guess the word I wouldn't really need to find much information. So let's just say it'll have a very high similarity with itself, but no similarity between like or cats. And the word like, who's liking, what am I liking? It'll probably have a high similarity between everything. And then the word cat, I don't know, will probably just have a high similarity between itself. So you can kind of see that the similarity matrix is formed between the words and itself. How are the words, or the vectors of the words, how similar are they to the query vectors? And this representation is how you get your output matrix. It's pretty much just the similarity between the vectors up here, and it allows information to be routed from all inputs. So I like cats to this one output, and then all inputs to this next output, and all inputs to this third output through a similarity matrix, as shown here. And that's really all that the queries and keys do. It forms a similarity matrix between the query vectors and the key vectors, kind of finding relationships among the queries and the keys. And remember, O8 matrix would only find a feed forward, would only look at a vector by itself. This finds relationships among all vectors, which is why it's so useful. So it allows information to be passed from any vector to one vector to another vector, and so on. So it's very, you can move information around very efficiently. And then they take the softmax. So the softmax is essentially forming a distribution for each of these. So the word I would be a distribution where it'll be, so I like cats. So this top word I would form a distribution where there is a very high similarity between I and itself, and then very little similarity between like and cats. The word like, on the other hand, would have a distribution that is very different, where it has a similar similarity between all of them. And the softmax just forms a distribution, so it's between 0 and 1 and adds up to 1. And then the word cats would look similar to the distribution of I, just with the word cats much higher. So that's what this matrix is doing here. That's what this query key matrix is doing. It's routing information from just the sequence to the sequence itself, and it's finding similarities between the words. And then you can multiply this by the values, and the values don't even have to go through a feed-forward layer. You can just send them straight through, and the values times this matrix is just changing the representation of the matrix in a way. It's just finishing the routing of information. So, and that gives you your output. In a way, it's kind of like this is a feed-forward matrix. So you can kind of think of it like I have an input. So I like cats. And this would be a vector of shape. That would be 3. And that would be E. And then it's a feed-forward matrix along the BS equal to 3 along the S dimension. So you send that through, and then you get an output, which is of shape S by E. So you can kind of think of it as a feed-forward matrix along the sequence, as opposed to what I showed at the beginning, where it's a feed-forward along the embeddings, and it allows you to mix information along the sequence, but it also computes it dynamically, because sentences, you want to compute the query key matrix dynamically, as opposed to it just being a static matrix. A static matrix can only do so much. A feed-forward matrix is a static matrix, and it can only do so much. But a dynamic matrix allows it a lot more freedom to find information in a sentence. So, and let me go up to where they formalize this. Right here. So you compute the queries, the keys, the values, you multiply them, that gives you your query key matrix, which is S by S. That's your similarity matrix. You can mask it, which I will get into later. And then you softmax it, that just forms a distribution, and then you matrix multiply it to get your output representation of the input sentence, your weighted output representation. So they also do this thing called multi-head attention. And multi-head attention allows you to do attention multiple times. So one attention is given a sentence, S is equal to 3 by E, I like cats, so your input sentence. You send it through attention, and then you get your output sentence, or your output sequence, S is equal to 3 by E, and that's your output. And that's just one, you only compute one similarity matrix, only one S by S matrix, the query key matrix. But if you have, what you can do is you can create multiple of those matrices. So if I can compute, so remember I feed them through a feed-forward layer, I get the queries and the keys, or queries, S is equal to 3, keys, and then the values. What I can do is I can break up the query keys and values into multiple matrices by splitting along the encoding dimension. And that'll give me, say I break it into 2, or say I break it into 4. So that'll be E over 4, S is equal to 3. This would be query 1. And then I have query 2, and so on. And each of them are E by 4 by S equal to 3. So you have this query matrix that is transformed into 4 mini matrices. Query 2, query 3, and query 4. And you do that for the query keys and values. So then I have these mini queries, query 1, mini keys and mini values, which I guess I can, so each of these are kind of a smaller matrix that's a slice of the query keys and values, and then you perform attention on those. So you'll form your query key matrix using queries times keys, or queries inner product keys, and then you multiply. I'm skipping the softmax normalization, but those are there by the values, and you get your output sequence, which is S by E over 4, because remember we split it up. And if you do this for all queries and keys, all 4 of them, then you'll end up with 4 of these output matrices, S by E by 4, and so on. So now I have this sequence, which I'm going to show on the left. I have this sequence, which is S by E by 4, S by E by 4, and you have 4 of these, and so on. And then you can combine them by just like attaching them together. So you can kind of stack this one on top, and then stack this one on top of that one. And then you have this longer matrix, which is E by S. So, in each of these, this was attention 1, this is attention 2, attention 3, and attention 4. So you just stack them on top of each other. And then you send this through a feed forward layer to kind of figure out how information in the embedding dimension, which was just concatenated together, can be routed. And then you get your original vector, which is S by E. And that was what we started with. So you split up, so multi-head attention splits up the queries into multiple queries. It splits up the keys into multiple keys into this. It's the same number, and in this case it was 4. It does attention on the on the slices, so the query 1, the key 1, and the value 1. Query 2, the key 2 and value 2. It concatenates them together. It projects it through a feed forward matrix, and then you get your output representation. And intuitively, what this may do is you may have different heads looking. So they call this heads, multi-head attention. So I'll show you up here. So you have a query, or you have the values, the query keys and values, which are of shape S by E, and then you split them up into 4. And here it's some arbitrary number. So you split them into H number of query keys and values along the E dimension. And the example was 4. You do H attentions, you concatenate them, and then you throw them through a linear layer. And you can think about this H, so each attention matrix, or each attention mechanism, as kind of finding some different information about the sentence itself. So maybe one's looking for verbs, maybe one's looking for, nouns, and it finds information among this, or it finds information in the sentence about those particular types of words. And that's what each head may do. And if you do that at the same layer, it's better than doing that at multiple layers, because you can get all the information at this layer that you need to then give to the next layer, which may find which may find more information about the different types of nouns, maybe more fine-grained information. And this is arbitrary. It's probably not going to find information about nouns. It's some hidden representation that we can't exactly understand, but intuitively to us, we may do something like that. We're given a sentence, we may pick out the nouns, the verbs, and then, and that's what each head may do. One head may pick out nouns, one may pick out verbs, and so on. And that's what multi-head attention does. So instead of just using one attention mechanism, you can use multiple at the same time in parallel, and the input and output matrices are the same. So this is S by E, and the output's S by E. So that's your output, that's your input. And same with this one. Input is S by E, and the output is also S by E. Output. So there's kind of no reason not to do that. It allows the attention mechanism to have more freedom in what information it kind of picks out. And that is how they do their attention mechanism. That's the really important part about this this architecture. And that's what you can see in these orange boxes, that they have this attention mechanism. So I'm just going to keep looking at this part right here. We'll get into the larger structure in a sec. So with this gray part right here, you have, I'm going to draw it out to the left. So you have this sequence that you input, S by E. You feed it through attention. So it'll go through attention. And notice how they have these three things here. This represents queries, keys, and values. That's why they have the three arrows as opposed to like one going into feed forward. So you have attention, and then you add a norm. So I'm just going to normalize. So you normalize, and they use batch norm here. I'm not going to get into how batch norm works, but it essentially normalizes statistics that the output distribution isn't some crazy number. So you normalize it to 0, mean, and variance 1, and then you allow it to choose the mean and variance that it wants to go to from there. I'm not going to get into how that works, though. And then you add the residual from before the attention mechanism to the output of the normalization. Residuals are in every architecture. They're found to help the model learn. And you can kind of think of it like if I were to just have this norm and attention, then it has to change the sequence, and it doesn't. But with the residual, it can kind of change the input sequence. So, sorry. Whenever you're sending it through here, it has to change the sequence, but it doesn't kind of know where it was coming from. So if it instead wanted to use the original sequence and change that a little bit, then it has the residual to do that. But it can't do that here. So, but better than that, it allows gradients to flow better. And it overall just helps the model in general. You can think of it as changing the input information as opposed to creating new information and outputting that. The residual is kind of like changing the information before the attention mechanism. And that's kind of why you have a residual. I mean, there's a whole paper that goes into how that works. So not going to go too in depth with that here, but it helps the model. And then you throw that through a feed forward layer. You normalize it again using batch norm. You add it, you add the residual, and then you output. And you do this over and over again. So I would have another block here, which would have the attention and so on. And then you keep doing this over and over again. And then that's your input block and that's your output block. But so we have that, and I want to go into this residual or this feed forward part real quick. And then we can get into the architecture. The feed forward part is defined here, where they use a ReLU activation function, and they use two-weight matrices. So what they do is they have a sequence, so it'll be S by E, and then you project that using a feed forward matrix, or a feed forward layer, to a dimension that is 4 times larger, so 4E and S, and then you apply ReLU to it, just an activation function. Then you apply another feed forward, which goes back to the original shape, S by E. And this is using an inverse bottleneck. So it you can think of the information as going from some small place to some larger dimensional space to the same size. So it allows information to be, it's projected to a higher dimensional space, and since it's usually easier to work in higher dimensional spaces, that's probably why they do it. And it kind of prepares the information for the next layer. And notice how the feed-forward layer is applied on the encoding dimension. It doesn't do anything about sequences, so it just prepares each token individually for the next part, for the next layer. So this would output the S by E matrix, and this feed-forward layer is preparing it for the next transformer layer, which would then do attention and so on. So that's what that's doing. And it just prepares each token individually because it's applied on the encoding dimension, not the sequence dimension. So yeah, so we've gone over this block, and we've gone over the attention, we've gone over the feed forward. Now let's go over how the encoder-decoder works. So let me erase this. All right. Remember how we had an encoder and decoder in the RNN. So you have this encoder that encodes the sequence, and a decoder that decodes the sequence. This is the attention mechanism is going to do that. And the way it works is by, I'm going to abstract it a little bit over here. So you have this encoder, and then you have this decoder. I'm going to make larger, but it'll just be easier for me to draw. So you have this sequence I, like cats, and then so that's S by E, S is equal to 3. So it's this three vectors, or three-part matrix, and then you feed it through the encoder, and the encoder will output a sequence of the same shape, S by E, and this is just an encoded representation of the input sequence. Remember here how we had H3, except this was a vector. In this case, it's a matrix, so it allows for more representation, and it kind of has multiple tokens. This is S by 3, and it kind of has a representation. Maybe it has a representation for each word in there. So like this would be a new representation for I, like, and cats. Maybe it has information for, like the new representation of like would be what is liked, who is liking, which is what the similarity matrix above kind of showed. I am liking, and I am liking cats. So maybe the like vector will have a new representation of that. But anyways, this is just the hidden representation H, call it H. And the decoder will decode the sequence one at a time. So you give it a start token, and a start token is just a vector. So the vocab will have a start token in it as well, along with an end token, which signifies that it's done generating the sequence. So you have this start token, so S will be equal to 1. So you have a matrix that is a 1 by E matrix, just like the I like cats matrix. And you feed this through the decoder, and the decoder will output a sequence that is also 1 by E. And the decoder also uses information from the hidden representation. We'll get into how it does that, but anyways, so you give it the input sequence start, which is just telling it to start, and it's decoding this start token into what the new representation will be. So, and it does that using information from the input sequence. So it outputs this 1 token because it's just a one-dimensional input sequence. And then you take this token, which I'm gonna represent like that, 1 by E, and then you project it using a feed-forward layer to a space that is 1 by v, that is e by 1, v by 1. And remember, v is the vocab size. And this kind of represents a distribution over all words in the vocab. So, what was it? It was me, gusta, gatos, perros, well, I don't know, some Spanish words, and we so since we have the start token, I'll give it also yo. So some Spanish words, and since we're translating to Spanish, our vocabulary is a Spanish vocabulary, not an English vocabulary, the output vocabulary. And then start and end. Those are in the vocabulary as well. So it also is part of the output sequence. And you apply this feed forward plus softmax. So you take this vector, you feed it through the decoder, it outputs a vector. You project the vector from a dimensional space that's lower than E. So E may be like 5 or maybe like 2. Let's just say this is a 2-dimensional vector to this 8-dimensional vector of shape of the vocab, because vocab is equal to 8, we have 8 words, and then you normalize it using softmax to get a distribution. Say the distribution looks like this. Maybe a little bit of that, probably none of that, and I don't know, maybe a little bit of end. So the distribution looks like this, and this is just represented by the vector here. And the distribution represents how likely the next word is, or how likely each word is to be next. So the word me and yo are pretty likely, so, and we sample this. We sample the distribution, and we take, so say we sample the distribution. So we sample it, and we get the word me. And then you add that to the input sequence, which is a new vector. So that now our sequence is 2 by E, and you repeat the cycle again. So you take this sequence, you throw it through the decoder. The decoder outputs, in this case, it'll be 2 vectors, which are 1 by E, 1 for each of the input tokens, and you take the last vector, and then you project that. So instead of taking this first vector, which was the start vector, we take the me vector, and you project it to the vocab size, and then it outputs a new distribution. So let's say the new distribution looks like this. Probably a little bit of me, probably a really good amount of gusto, some gatos, some perros, maybe some mo, no yo, no start, maybe a little bit of end. Then we sample it, we get gusta. And then we throw that back in, gusta, and that's a new vector. So now this is S, E is equal to 3, so it's a 3 by E matrix. We throw it through the decoder, we get another vector output. And we keep doing this, so we will get gatos, and then we'll get end token, signifying the end of the sequence. So you'll feed this sentence through a total of 1, 2, 3, 4 times, or 5 times. Well, I guess 4 times. So you'll feed the start token through and get the me token. You feed the start me, and you get the gusta token. You feed start me gusta, you get gatos, and you feed start me gusta gatos, you get end, and then you're done. And that's how you generate your sequence. And remember, it has information of this hidden state, which is a representation of I like cats. And that's how the encoder-decoder style works. And that's what they have up here. So this is the encoder on the left. This is the encoder, and this is the decoder. So you have this sequence that is of shape S by E. Don't worry about positional encodings right now. Get into that in a sec. You feed that through. You feed this through n different encoder blocks, and you get a sequence that is S by E output. And then you feed a sequence that is 1 by E. This will be the start token. You feed that through. You get an output. You get an output distribution. So it'll be some distribution over the vocab or it'll be the Spanish vocab. So some distribution over me, gusta, blah, blah, blah. Some distribution, you sample that, you add it to here. So now it'll be S is equal to 2. You feed that through. You get another distribution output, looks different. You sample that, you throw it back in here, and so on. And then until you get your end token. And that's how you get your, that's how you encode the input sequence, which is I like cats. And you get an output, which is me gusta gatos, with start and end tokens. So that's the encoder-decoder. There's a little more to that, because notice how there is what's called cross attention. So notice how in the encoder it's query. So this is a query, that's key, and that's a value. Notice how it's just all go, like the input sequence is directly going in there. Here, on the other hand, it's query key value, where the value is coming from the decoded sequence, the Spanish sequence, and the input, or the queries and keys, are coming from the hidden representation. So this is a way of mixing information between the inputs and the outputs. So this masked multi-head attention, don't worry about the mask part, we'll get to that in a sec as well. This masked multi-head attention finds relationships between, so queries values, between the output sequence itself, the me gusta gatos. So that's just normal old attention, don't worry about the mask, normal old attention that you do between the sequence and itself. The cross attention right here computes the query key similarity matrix between the hidden representation, H, and then projects that, and then projects it to the value matrix. So it's a way of mixing the information between the output sequence and the hidden representation of the input sequence to condition the output sequence on the input sequence a little bit. Otherwise, it would have no idea what it's trying to do. Otherwise, it would have no idea that it's trying to decode, I like cats. So, and then it just feeds it through a feed forward layer to get it ready for the next layer. That is, so that's kind of how the encoder-decoder works. And that's how they mix information between the encoder and decoder. Now for the positional encodings. So positional encodings are, like, one problem with attention is it works on unordered sets. So the sequence I like cats will have the output sequence, which is of shape 3 between the queries and the keys. And this query token, it looks at each part of the input sequence, but it doesn't care. It doesn't care about the order. This is an unordered sequence. If I have like iCats, it would be the same. Or like cats I, it would be exactly the same representation. It doesn't matter. It doesn't care about the order. So that's a problem. To fix this, what we can do is add positional encodings, which give it positional information about where it is in the sequence. Where is that token in the sequence? So I like cats is 3 vector representations, and we can add a positional encoding to each of the vectors. Positional encodings work like so. You have multiple sine waves or cosine waves of frequency of increasing frequency. I'm not going to draw forth. So this will be f, frequency f. This will be, I don't know, frequency 2f, 3f, and so on. And you can sample them uniformly. So we'll sample this 3 times. And on the sampled locations, you get a value for the sine wave there. So, and we're sampling this 3 times because we have 3 vectors, I like cats, and we need positional information for all 3. So this would be position 1, 2, 0, 1, 2. And you form these vectors, and in this shape, the vectors will be of shape 3, because we have, I'll call this A, B, and C. We have 3 sine waves, so it'll be a 3-dimensional vector. And you store the values of the sine waves at those vectors. So at position 0, you may have, I don't know, looks like that is maybe 0.5. Maybe that's also 0.5, 0. And then you do the same for this one. I don't know, maybe that's 0.5, maybe that's 0, 0.1. And 0.1, 0.5. So you have these 3 vectors. And then what you do is you add the vectors to each of the, so you add the vectors to each of the parts in the sequence. So you add it to the vector I, like, and cats, and the number of sine waves has to be equal to the encoding dimension of each of the vectors. So you add it, and then you get a new vector representation. A better diagram would look like so, where we have the 3 vectors. That'll be I, like, cats. So we have the these are the words, and then we have the vectors for the positional encodings, and you add them and you get new vectors, which are the outputs, which are the words plus the positional encodings. So now each word has a unique positional encoding representation that the machine learning algorithm can figure out by itself where it is in the sequence. But now it has information because this part right here, the 0th item in the sequence, will always have the same sampled frequencies or the same sampled sine values added to it. And the machine learning algorithm can, or the attention mechanism can figure that out. So that's how you can add positional encodings, and it does that for both the input sequence and the output sequence, and the output it does it to the output sequence after every word, because it has to know, it has to have a positional encoding for each of the words. So now, finally, we have the masked multi-head attention. So let's go into that. So one problem with the encoder-decoder style is I have this hidden representation. I have the decoder, and then I have the token start. And then to get the output sequence, I have to feed this through many times. So this will give me the word me. So then I'll have me, and then I'll have Gusto. Then I feed that through Gusto. Then I would get the word gatos. And then you keep going, and you have to do this s times, where s is equal to the sequence length, and that takes a while. You don't want to do that, and during generation time, it doesn't matter. You can't bypass that because it's inherently sequential. But if you can actually bypass this in during training, which is very nice. So remember the query matrix, which is of shape S by E, the key matrix, which is of shape S by E, and the value matrix, which is also of shape S by E. The queries and the keys form I'm going to keep it as a 3x3 matrix with the I like gatos, or I like cats example. I like cats, and I like cats. And so the queries and the keys compute that matrix, the query key matrix, which is the similarity matrix. And say I want to make this parallelized. And say I want to, so if I parallelize this, then given the word I, or actually in this case it would be me gusta gatos because we're decoding. So me gusta gatos, me gusta gatos. Sorry. Yeah. So in this case, yeah, it would be Spanish because we only care about the decoder part. The encoder part needs to know all the information. So if I were to give it the word me, it doesn't know about the words gusta and gatos until it generates it. So if I just had the sentence me, then we don't want it to look at the future because that would kind of be cheating. So say I give it the sentence me, and I wanted to generate gusta and gatos. Whenever it's doing a translation, so if I just give it I like cats and it has the word me, it won't have the context of gusta and gatos until it generates that. So we want to kind of simulate this. And to do that, we can mask out the future tokens so that it can't look at those. So in this case, me can't look at gusta and gatos because it hasn't generated that yet. But whenever we get to gusta, it'll have information of gatos. And if we mask it, then we can actually parallelize this whole sentence. And to mask it, all you do is you add, so the black boxes will be negative infinity. And whenever you softmax that, it'll be 0. So in this case, this distribution will look like this, where it's 1 and then 0 and 0. And then this distribution will look, I don't know, like something, and then 0, and then this distribution can be anything. The distribution is the routing distribution between these words. And notice how the distribution of me cannot possibly route information from gusta and gatos. It can only route information about itself because it's, well, the only part of the sequence so far. And gusta is the only part of the sequence, or me and gusta are the only parts of the sequence, not gatos at that point. So we're kind of simulating the generation sequence. Or we're kind of simulating generation, but in parallel, because remember, this matrix is computed given the sequence me gusta gatos. And it only does that here. So we don't do it here because we want to know all information about I like cats. Like whenever we're translating, we know the word, we know the entire sentence I like cats. And then whenever we're decoding, we only know one part, we only know the sequence, we only know the past. And that's what the mask does. The mask only allows it to look at the past. And then here, the queries and the keys are computed from the hidden matrix, which is the input matrix. And since we know everything about the input matrix, we don't need to mask it. So this isn't masked. So that actually allows us to compute stuff in parallel. So given that, we can train it so that we give it the sequence I like cats, feed it through the encoder, and then we get the hidden representation, S by E. And then we have the decoder. And to train it, remember, this is only for training the masking part, because it doesn't matter for the generation part. It's inherently sequential. We don't know the feature, but we know the feature for whenever we're training it, we know what we want to generate. So we use the gatos, and this will be S by E. We feed that through with masking. And remember, we get a sequence out that is S by E. So S is equal to 3 by E, which is 3 vectors. So that'll be a 1 by E vector. That'll be a 1 by E vector. That'll be a 1 by E vector. And if the masking is done right, then you can independently make a distribution for all of these, where this first vector, this first one, represents the output distribution, so whatever that is over the vocab, for just the word me. And the second vector represents it for the words me and gusta, and the third vector represents it for me gusta gatos. So instead of doing this sequentially, we can do it in one step where we feed the whole sentence through the decoder, and we get all the output tokens. And then we use all the output tokens this time instead of just the last one. And we use each of these tokens as the distribution at that time. So that would be me, that would be gusta, and this distribution would be the one that we want to output gatos or gusta. This distribution would be the one where we want it to output gatos, and then this distribution would be and this is a v by 1 because you project it, a v by 1 vector would be the one that outputs the end token to end the sequence. And you can use this output and you can parallelize the output. So you're training in parallel as opposed to training on one word at a time, which is very slow. And that's why they mask it. They do a lot of really cool things in this paper, and that's one of them, the positional encodings and just the attention mechanism in general. It's all really cool. And that's how the encoder-decoder works. Finally, I want to get into two different, one of the problems with attention and some of the results. So one of the problems with attention is it's an n squared operation. So if we have a sequence of if we have a sequence of shape S, then the query key matrix will be of shape S by S. So imagine I have a sequence that's 512 by 5 or 512 words. Then you have this massive matrix that's 512 by 512. That is a lot to store. And especially if you get up there to 2048, that's a lot of memory. And it's also complexity in terms of time as well. So it's complexity in terms of time and memory. So you have to store this whole thing, and it takes a lot of time to generate the query key matrix and the attention mechanism. And that's one of the drawbacks to it, which a lot of papers go into trying to fix that. And in case you're wondering, that's the positional encoding. That's how they do it. And I simplified it a little bit, but that's how they do it. But yeah, anyways, that's one of the problems with attention. And then the results, let me find those. The results are really good. Oh, those are here. So the transformer pretty much outperforms everything. And surprisingly, it does so with less flops, but in reality, it has more flops than architectures now. This is a 2017 paper. And I don't know, it just shows how powerful this is, because before it was like 24, 25, 26. Those were the scores, the BLU scores. So higher is better. BLU is so in this case, I think that's English to Dutch, English to French. And the higher the score, the better the translation is. And you can see that it's getting a lot better results than the rest. So it just shows how powerful this architecture is, and it's why it's built into everything. So that is attention is all you need. Let me know what you think about it.